I greet everybody at lecture on biophysics. This lecture is on quantum mechanics principles of medical imaging methods. The lecture goals are identification of physics phenomena, medical imaging methods based on. And number 2, specification of physics processes into tissue registered and converted into tissue images. The objectives of the lecture are these. First of all, it will be quantum mechanics basics review, and secondly, it is physics principles of objects internal structure imaging. The lecture points are listed at this slide, and we start from the number 1. It is introduction, quantum mechanics basics of atom structure. I greet everybody at lecture on biophysics. This lecture is on quantum mechanics principles of medical imaging methods. The lecture goals are identification of physics phenomena, medical imaging methods based on. And number 2, specification of physics processes into tissue registered and converted into tissue images. The objectives of the lecture are these. First of all, it will be quantum mechanics basics review, and secondly, it is physics principles of objects internal structure imaging. The lecture points are listed at this slide, and we start from the number 1. It is introduction, quantum mechanics basics of atom structure. Quantum mechanics is the science dealing with the behavior of matter and light on the atomic and subatomic level scale. It attempts to describe and account for the properties of molecules and atoms and their constituents, that are electrons, photons, neutrons, and other more esoteric particles such as quarks and gluons. These properties include the interaction of the particles with one another and interaction of the particles with light, X radiation and gamma radiation. Today we consider the quantum mechanics approach suggested by Erwin Schrödinger, who developed a procedure for constructing the wave equation for a particle or system of particles, if forces acting among them are known. This equation you can see at this slide, and Schrödinger's equation determines the quantum mechanics wave function. Its absolute value squared is proportional to the probability of finding the particle at particular point into the space. Hydrogen atom is the atom to discuss in context of the Schrödinger equation. It is found that each allowed configuration of any system has a unique wave labeled by certain values of the quantum numbers. In the solution of the Schrödinger equation for the hydrogen atom, 3 quantum numbers arise from the space geometry of the solution. A fourth arises from electron spin, no two electrons can have an identical set of quantum numbers. What are that quantum numbers? The first, it is the principal quantum number that is marked by symbol n small. And it is any integer starting from 1. The next, it is the orbital quantum number that is starting from 0 up to n minus 1. Magnetic quantum number is or for 2l plus 1 values. And finally, spin quantum number. For half spin particle, that is electron, it might be plus 1/2 or minus 1/2. Let's consider more detail that quantum numbers. The principal quantum number or total quantum number n arises from the solution of the radial part of the Schrödinger equation for the hydrogen atom. The bound state energies of the electron in the hydrogen atom are given by the equation shown at this slide. The basic hydrogen energy level structure is in agreement with the Bohr model. Common pictures are those of a shell structure which each main shell associated with the value of a principal quantum number. In the notation of the periodic table, the main shell of electrons are labeled by K for principal quantum number equals to 1, L for principal quantum number equals to 2, M for n equals to 3, etc. Based on the principal quantum number, the shells may be labeled by letters. Similarly to an object that performs a rotational motion, each electron in an orbital is characterized by an orbital angular momentum. It is marked by capital L. The electron can have a definite magnitude for the angular orbital momentum, but not a defined direction. The angular momentum quantum number L small describes the shape of the orbit as that an electron occupies. When L equals to 0, the angular momentum quantum number, the angular momentum of the electron, L capital, is 0 as well. The atomic orbitals which describe these states are called s orbitals. The s orbitals are distinguished from one another by starting the value of the principal quantum number n. They are referred to as 1s, 2s, 3s, etc. atomic orbitals. So now we recognized two quantum numbers. The first principal quantum number, that is the not measure but actually number determining the energy amount of the electron into the atom, and orbital quantum number determining the shape of the orbit of the electron into the atom. All s orbitals predict spherical density distribution for the electron. The ground state of a hydrogen atom, n equals 1, L small equals 0, has a probability cloud describing the position of its electron. The probability of finding the electron is proportional to the darkness of the cloud, as it is shown at the diagram in this slide. The electron can be closer or further than the Bohr radius, but it is very unlikely to be a great distance from the nucleus. To say an electron is in particular orbital is meant to imply that the electron is in the quantum state which is described by that orbital. For example, when the electron is in the 2s orbital, the hydrogen atom is in a state for which principal quantum number n equals to 2 and orbital quantum number L equals to 0. When we talk about an electron that is orbiting into the atom, this looks like the loop carrying electric current, because electron, it is an electrical charge that goes along the trajectory, along the orbit into the atom in the only one direction. So consequently, this may be modeled as a loop carrying electric current. So when this orbiting electron is placed into the magnetic field, it would behave itself as the magnetic dipole. It will be orientated by forcing of magnetic field. An electron with an orbital angular momentum L capital is effectively a current loop or a magnetic dipole. An electron of charge minus e and mass m moving in an orbit with angular momentum L has a magnetic dipole momentum that is proportional to orbital angular momentum. This relation you can see given by the formula. The energy of the loop depends on its orientation relative to the external magnetic field. The energy of the dipole in magnetic field may be calculated by formula shown. And here you can see this combination of the parameters mu, magnetic dipole momentum, times cos theta. This is just the z component of the vector mu. So z we take as the axis, and at this direction the magnetic field is considered directing as well. It is found that the component of the electron angular momentum Lz along the direction of the magnetic field that is marked B at the electron location, usually called the z-axis, can have only allowed values, angular or orbital momentum of the electron can be of that allowed magnitudes. The magnetic quantum number m with the index L can have any of 2L plus 1 integer values for a given value of L, orbital quantum number. If the z component of angular momentum can have only certain values, then the angular momentum vector can have only certain directions. Since angular momentum can only have certain values, magnetic momentum also have specific allowed values. What are that? Possible magnitudes are shown by the formula relating mu z and z component of angular electron momentum. The resulting electron energy levels in the magnetic field are given by this formula you can see. The electron has an intrinsic spin angular momentum with an associated magnetic dipole momentum. We can imagine to ourselves that electron into the atom not only orbiting around the nucleus, but also it is spinning. It is kind of rotation around axis crossing the imagined center of the electron. And consequently, we should take in account this specific intrinsic property of the electron as the spinning, and spin angular momentum is determined by the electron spin quantum number that equals 1/2. In atomic structure, it is the z component of the spin angular momentum that is important. For a spin 1/2 particle, this z component equals to this magnitude that is shown by the formula. And m letter with the index s is just the magnetic spin quantum number that is of two possible magnitudes plus 1/2 and minus 1/2. Despite the fact that electron spin never points directly along the axis z, the two states with ms equals plus minus 1/2 are often referred to as spin up, ms equals to 1/2, and spin down, ms equals to minus 1/2. Thus, for every set of values for n, l, and ml, there are two allowed values of ms. The allowed electron orbits are assigned a quantum number n that runs from 1 for the orbit closest to the nucleus to infinity for orbits very far from the nucleus. All of the orbitals that have the same value of n make up a shell. Inside each shell, here may be subshells corresponding to different rates of rotation and orientation of orbitals and the spin directions of electrons. In general, the further away from nucleus a shell is, the more subshells it will have. You can see here the illustration of the configurations of the electrons into atoms of some materials, of some substances, from the periodic table of the substances. Now let's consider this phenomena, that is the quantum jumps. Heat or other stimuli may cause an electron to break out of its energy band and jump over one or more energy bands down to a lower energy orbit, releasing a portion of the energy that is named as photon, with a quantum of energy corresponding to the difference in energy level between the two orbits. It is the photon emission. It is not the continuous way of the electron from orbit to orbit. It is just the jump of the electron, and when we talk about emission, from the higher energy level to the lower one. Conversely, when photons collide with an atom, their energy may be transferred to and absorbed by the atom's electrons, causing them to jump to a higher energy level orbit. It is the photon absorption. The frequency of the light energy released or absorbed in the quantum jump is given by Planck's law. Energy equals to the product of the Planck's constant and the difference in energy levels between the initial orbit and the final orbit. The corresponding wavelengths of the photon may be calculated by formula. Lambda equals the speed of light, in particular speed of light in vacuum, that is marked by letter c, over the frequency. Each element has a unique set of atom electrons' energy levels. The energy is released or absorbed when electron jumps from one discrete energy level to another. So, the frequencies at which electrons absorb and emit light act as a fingerprint identifying the particular element. The spectral lines of light emitted by an atom are known as its characteristic frequencies. The allowed energy states of some substances, atoms, make these atoms capable to radiate electromagnetic waves with unique characteristics. These are used as laser media. And now let's consider how this quantum mechanics approach to describe the atomic structure of the substance works when we talk about the substance to be able to generate the laser radiation. We start the second point of our lecture. It is the laser radiation applications in medicine. Laser is actually an acronym for light amplification by the stimulated emission of radiation. Stimulated emission depends on changes in the energy of electrons orbiting the nuclei of the atoms of the lasing medium. Two important conditions must occur in any laser. One is called population inversion, and the other is called stimulated emission. The energy 3 levels laser medium is required for this. In a continuous laser, atoms are continuously pumped from a low energy state to a larger one. These excited atoms then don't return to the initial state, but instead fall into an overpopulate a third state of intermediate energy. The laser action then takes place between this third level and some lower state. One continuous laser producing light at 632.8 nanometer contains a mixture of the helium of 80% of the mixture and neon of 20% of the mixture. These are gases. This laser diagram is present in the slide. The high voltage electric discharge between cathode and anode excites helium atoms, electrons to higher energy levels. The helium and neon atoms have field N1 and N equals to 2 electronic shells respectively. When these atoms are excited, the electrons must return to a 1s state in helium and to 2p state in neon to re-establish the ground state. The 2s, n equals to 2, and orbital quantum number equals to 0 level in helium is of 20.61 electron volts energy above the ground state and is lower than 2p state, n equals to 2, L equals to 1. When an electric discharge occurs in the gas, electrons that end up in the 2s state in helium can't return to the 1s ground state because the orbital angular momentum of the two states is the same. The 2s state is metastable. The electrons are stored at this energy level. However, the 5s state of neon happens to be 20.66 electron volts above its ground state. Thus, one way that electrons in helium can return to their ground states from the 2s state is by colliding with the neon atom and exciting a neon electron from 2p state into 5s state. The slight energy difference is made up by thermal kinetic energy of the helium atom. In an effect, the continuous fund of 2s electrons in helium is pumping electrons into the 5 state of neon. The laser action then occurs when the electrons of the 5 state of neon falls into the 3p state, emitting photons with the wavelengths 632.8 nanometer. So you can see how quantum mechanics principle describes and supports the procedure of laser generation. The other coherent transitions can also occur, but none are in a visible spectrum. This you can see at the diagram of this slide. If a system of atoms is forced into having the higher energy states overpopulated, the emission of a single photon during a transition to the lower state by one atom will trigger the emission of photons by many more atoms. A schematic diagram of laser in the slide shows the helium-neon mixture placed between fully reflective and partly reflective mirrors. The neon atoms is in normal state are shown at the first diagram. The diagram 2 shows population inversion achieved. This is done by feeding energy into the neon atoms by collisions with the helium atoms, and often called pumping. Photons are emitted by random neon atoms, as shown in the third diagram in the slide. Some photons are lost through the sides, but one is shown initiating stimulated emission perpendicular to the ends. After partial reflection, the build-up of coherent photons constitutes, as it is illustrated by the diagram under number 4. The build-up continues after total reflection from fully reflective mirror. At the diagram 5, it is shown that the 1% of very large number of photons present escape through the partly reflective mirror. The behavior of laser medium atoms determines the unique laser radiation characteristics. These are highly monochromatic. Laser radiation is coherent, highly directional, and can be sharply focused. The laser media for medical applications are listed in the table in the next slide. The videos will support this description, and you can look at these fragments.
Pumping and population inversion. As we've already said, the transitioned electrons don't stay for longer time in the excited state. There are electrons of some substances or systems where they remain in the excited state for longer period. Such systems are called active systems or active media. These are generally compounds or mixtures of different elements. When electrons turn into active systems, their electronic energy levels are also modified, and thus it acquires some special properties. Now, let us discuss them in detail.
Now, let us consider an atom has 3 electronic states,
E1, E2, E3 in active medium. Generally, electrons exist in lower state called as ground state E1. Let us number of electrons in ground state as N1. As we have already learned, due to the process of absorption, when electromagnetic energy equals to the difference of E3 minus E1 are incident on atom, electrons jump from state 1 to the excited state 3. Due to the process of spontaneous emission, the excited electron in the E3 state remains for less period, in order of 10 power minus 8 seconds. Usually, most of the electrons loses its energy due to spontaneous emission and returns from E3 state to E1 state. The number of electrons in this state is said to be as N1, but some of the electrons may lose very less energy, E3 minus E2, and jump to state E2. The less emitted energy by electrons is called as thermal energy. This energy is absorbed by the medium itself. The transition or jumping of electrons from E3 state to E2 state is called as non-radiative transition or invisible transition. The electrons in this state, E2, remains for longer period compared to state E1 in the order of 3 into 10 power minus 3 milliseconds. This electronic state is called as metastable state. The number of electrons in this state is said to be as N2. The number of electrons N2 in the state E2 will be increasing rapidly. At some point, number of electrons N2 has more number than the number of electrons N1. That is, N2 is greater than N1. This stage is called as population inversion. The process in which the number of electrons N2 in a higher energy state called metastable state of an active medium is increased to a value greater than the number N1 in the ground state. That is, N2 greater than N1 is called as population inversion. How could we achieve population inversion? Population inversion is achieved by the supply of sufficient and appropriate energy to the active medium from an external source. Thus, the process of achieving population inversion is called as pumping. Induced and stimulated emission. Earlier, we had learned that electrons remain for longer periods in the metastable state, that is 3 into 10 power minus 3 milliseconds. Now, let us assume coherent beam of light energy h nu is equal to E2 minus E1 incident from an external source on the active system. The light energy in the form of photon stimulates electrons in the state N2 to undergo transition to the state N1. The large number of photons of same energy is simultaneously emitted. Thus, the emitted photons have the property called as temporal coherence, and this process is called as induced or stimulated emission. When an active medium is in enclosed state, multiple reflections of emitted light occurs, where stimulated emission dominates spontaneous emission. Thus, the incident beam of light gets amplified and results in output as laser, light amplification, stimulated emission of radiation.
Everyone has seen them, and have probably teased many cats with them. Maybe some of you have had unwanted hair removed. Or maybe you have built one and popped some balloons with it. Bottom line, lasers are ubiquitous not only in scientific research but also in industry. Just how do these little devices manage to put out that nice powerful collimated beam of light? All this and more coming up. As some may or may not know, laser is actually an acronym. It stands for light amplification by stimulated emission of radiation. However, nowadays it is so common that people don't bother to capitalize it and simply write laser. A very brief history of the laser starts in 1917 when Einstein introduced the concept of stimulated emission, which will be explained shortly. Then in 1954 the first maser was demonstrated by Charles Townes. The M standing for microwave. The ammonia maser was the first device based on Einstein's predictions and obtained the first amplification and generation of electromagnetic waves with a wavelength of about 1 centimeter, which is in the microwave range. This is recognized as the precursor to the laser. It wasn't until 1960 when Theodore Meyerman developed the first working laser at Hughes Research Lab. Meyerman's early laser used a powerful energy source to excite atoms in a synthetic ruby to higher energy levels. The development of the laser was a collaborative effort by scientists and engineers who were leaders in optics and photonics. Okay, so why are lasers useful? Why are they ubiquitous? The answer can be broken down to 3 unique properties the laser holds. The first being line width. The purity of a laser, referred to as the line width, can be quite narrow, more so than any other light source. In layman's terms, this is a measure of what frequencies are contained in the emitted light. The narrower the line width, the closer the emitted light is to a single frequency, single color if you will. Thus, a laser is said to be monochromatic. In reality, it does output a small range of frequencies. The smaller this range, the better the line width and quality of the laser. In contrast, an incandescent bulb has a very large line width and emits a broad spectrum, which is why the emitted light is white. White light is a superposition of all the colors in the visible spectrum. Having a narrow line width is useful because many scientific experiments want to analyze stuff with certain energies. Different wavelengths of light correspond to different energies, hence having a source with one energy is helpful. The second is coherence. The light emitted by a laser is coherent light. This means it is all polarized in the same direction as well as being in phase. The laser is said to output highly coherent monochromatic light. An LED, on the other hand, is also monochromatic, one color, but it emits incoherent light. An analogy with synchronization and harmony can be made. Imagine an orchestra playing. If the orchestra is in sync and everyone is playing the parts correctly, it will be pleasing to the ear, the laser. If some players are playing out of sync but still playing the parts correctly, it won't sound as good, the LED. Coherence is important because all the photons add their energies together, and we can then focus them on a small spot over some distance. Lastly, power. Lasers make it possible to deliver high-intense light to a small area. Of course, militaries are particularly interested in this aspect of the laser, as well as medical applications. Laser eye surgery, for example. Now let's take a look at how a laser works. The workings of a laser are quite complex, as it requires an understanding of quantum mechanics. There are some commonalities behind every laser. The first part can be broken down to 3 key pieces: stimulated absorption, spontaneous emission, and stimulated emission, which is what the SE part of laser stands for. Let's take a look at the first concept, stimulated absorption. We will need a nucleus that is made up of protons and neutrons that has an overall positive charge, and an electron that has a negative charge. Hey there, little guy. Most textbooks show electrons existing in discrete energy states of a material. But actually, electrons exist in probability density clouds around the nucleus, as they have wave-like behavior, and the orbitals represent the average distance one is likely to find it. Let's use this average distance to define the orbital, and ignore the probability distribution for simplicity. Mostly always, electrons are found in the lowest energy state, or ground state. Everything in nature wants to be in a low energy state, as it is easier for it to exist at this level. In other words, it minimizes energy. Think of a ball on a hill and how easy it is for it to roll down. It wants to roll down because the energy state is lower, closer to the Earth's core than further away, in this case potential energy. However, it is possible to excite electrons by some kind of external means. Just like we can exert a force on the ball that has rolled down and push it back up. Light can be this push to excite electrons. If a photon of light, which is 1 unit of light, comes across an electron in a low energy state, it can sacrifice itself, and push the electron to a higher energy state. The photon is annihilated, but the energy of it is now part of the excited electron. It should be noted that each material has different levels of energy. In other words, if the ground state is 1 unit and the next energy level is 5 units, then the photon of light must have exactly 4 units of energy to excite the electron to that energy level. Anything lower will not suffice and anything higher would not as well, as there is nowhere for that extra energy to go, unless a higher energy state exists. If the incident photon is very high in energy, the electron would be ionized. To continue our analogy, it would be like trying to push the ball up the hill with not enough force, the ball would just roll back down. Too much force and it would roll down the other side, go to another plateau, or be launched into space. An exact amount of energy is required to elevate it to a particular energy state. Again, this process is called stimulated absorption. As we are stimulating the electron and it absorbs the photon's energy. The next mechanism we will look at is spontaneous emission. We now have an excited electron. What happens now? Well, again, this higher energy level is quite unstable and after a very short time, about 100 nanoseconds of being there, the electron will eventually fall. For some perspective, light travels about 29 meters in 100 nanoseconds. When it falls back down it will release a photon with energy equal to the difference in energy levels. The higher the fall, the higher the energy of the photon will be. Should the energy value of the photon that is released be in the visible range, we would perceive it as color. You may be thinking, if the electron reaches the higher energy level through the previously mentioned stimulated absorption mechanism, why exactly does it fall back down? Well, referring back to the ball example, imagine the ball on a hill, but now with the top having zero friction, and a sharp point. The ball can remain there only if it is perfectly balanced, but any tiny little force in either direction will cause it to start rolling. The electron in this higher energy state is in a similar situation. The forces that push it are small perturbations in vacuum energy. This is a quantum mechanical effect. Space or vacuum is not as empty as we think. Things are popping into and out of existence constantly. It is these vacuum events that perturb the electron. This is also responsible for why things are ferromagnetic. That's a different story though. Again, this process is called spontaneous emission. As the process that the electron falls back down to the lower energy state is more or less spontaneous. The last quantum process we will talk about, and the most important for lasers, is stimulated emission. This occurs when a photon interacts with an electron that is already excited. This photon can act as a type of perturbation, and force the electron to fall back down to a lower energy state and emit a photon. We then will have two photons. Photons actually like to be together, so if one comes near a situation where another one could be present, such as the electron falling back to a lower energy state, the situation usually will play out. The important part is that the emitted photon will be identical to the one that stimulated it. Meaning same frequency, phase, and polarization. They will be coherent with each other. So, if we could somehow avalanche this process we would have a laser. After all, that is basically what a laser is. A zillion identical coherent photons being emitted. In contrast, if two electrons undergo spontaneous emission, the emitted photons will unlikely be traveling in the same direction, nor be in phase. But in order for electrons in the excited energy level to be able to undergo stimulated emission, and not spontaneous emission, enough time has to be available. The lifetime of an electron in the excited level is just too short. However, some materials have so-called metastable states. These are excited states with slightly lower energy than the excited states. These states allow the electron to remain there for much longer lifetimes, milliseconds instead of nanoseconds. Enough time that a passing photon can cause it to undergo stimulated emission. Of course, an initial spontaneous emission from the metastable state to the ground state must occur in order to have the initial photon that can stimulate other excited electrons in the metastable states. To sum up, if a ground state electron is hit with a photon, it will absorb it, and move from the ground state to the excited state. The photon must have the energy equal to the difference between these levels. This electron will then transition to the metastable state, if one exists. This transition does not emit a photon, and is said to be a radiation-less transition. The energy difference is dissipated in other ways, heat or phonons. Now this electron, If a photon stimulates it, will emit a photon with equal energy, phase, and direction. These are the ones that make up the laser beam. It should be apparent that the photon which pumps the electron from the ground state to the excited state has a different energy than the photons that are being lased. This is because the energy difference between the ground state and the excited state is different than the difference between the metastable state and the ground state. The pumping photons are always higher in energy than the photons being lased. We obviously want lots of electrons in this metastable state, more so than the ground state, in order for them to be in a situation where stimulated emission can occur. Something known as creating a population inversion is required. If we only had 2 levels, we would reach a point of saturation, where 50% of the electrons are excited, and 50% are not. The excited electrons simply spontaneously emit too fast. Essentially our medium becomes transparent to photons. By introducing the metastable state, we force the pumping photons to excite the ground state electrons, that then transition to the metastable state, so the photons that are emitted by the transition from the metastable state to the ground state are primarily used to stimulate other electrons in the metastable state. Enough time exists for this to happen. Yes, some of these photons will excite ground state electrons directly into the metastable state, but the pumping photons should take care of the majority, and create a situation where there are more excited electrons in the metastable state than ground state electrons, a population inversion. By the way, the above is describing a 3-level laser. 4-level lasers exist and are more efficient. Again, we want to create an avalanche effect, where the spontaneously emitted photon that was created when an electron transitioned from the metastable state to the ground state, gets amplified through the means of stimulated emission. We don't want just a single puny photon, we want lots, all working together. It is not practical to create a laser that is extremely long, so the solution is to put the laser medium in a cavity. Let's take a closer look at how a cavity will influence the light waves, and how exactly this will create the amplification we desire. Since light is a wave, it will be subject to constructive and destructive interference. We want constructive interference in our cavity to take place, in order to have a high-intensity beam. A laser cavity has a mirror on one side and a partial mirror on the other. It is partial because we want some of the beam to escape, that's the beam we see. Now when light waves are created through spontaneous emission, they will initially travel in random directions. But the ones traveling perpendicular to the mirrors will reflect back and forth. Let's take a look at one of these light waves. It is first emitted via spontaneous emission and quickly becomes large in amplitude through stimulated emission. It travels towards the mirror, and is reflected back. Because we continue to stimulate atoms in the left and right directions, we get 2 waves in the cavity. Again, one moving to the left, and one moving to the right. Waves will add their amplitudes when interfering with each other. In this case, we will get a standing wave. Meaning instead of a wave noticeably moving to the left or right, the combined wave will appear to be going up and down. Rest assured, this is just an illusion. This is the effect of 2 waves hitting each other head-on, and their left and right components cancel out, but their up and down components add together. So when the wave looks flat, this is a moment when the 2 waves are destructively interfering with each other, and at the maximum they are in a constructive interference point. Here are a few examples of some standing waves in a cavity that are resonating. Resonance is just a fancy word for having these waves being in a state where standing waves are being produced. A mode being just what n you have, n equals 1 is a mode, n equals 2 is another one, n equals 3, etc. Is there an equation that will tell us what modes can exist in the cavity? Sure there is. The left part is the frequency that exists in the cavity, n is the mode, which is always an integer, v is the velocity of the wave, and L is the distance between the 2 sides of the cavity. The velocity in our equation is the speed of light, c, which is 300,000 kilometers per second. The L is just the distance between the mirrors. Light traveling from the left of the cavity will now interfere with light traveling from the right. So again, we have these possible modes where the light can produce standing waves, and be in resonance. Not all frequencies are able to exist in a cavity, but a lot are. Also, let's be clear that the standing waves produces are a collection of trillions and trillions of light waves all working together. They are produced by stimulated emission, and the cavity allows them to keep amplifying each other. They are coherent with each other. Recall, this was one of the big reasons why we care about lasers. If we didn't have this synergy between light waves, we would just have an ugly LED. I bet you can't make your cat go crazy with a red LED. Well, maybe, but you get my point. Question: what frequencies are allowed to exist in a red laser pointer's cavity? Answer: a cheap red laser pointer has a cavity length of about 1 mm, and the speed of light is c. 300 million meters per second. Plugging in these values to our equation, we would get a difference between allowed frequencies of about 150 GHz. Now, red light has a frequency of about 400.05 THz, which corresponds to an N value of 2667. Recall N must be an integer. So if 400.05 THz is an allowed frequency, then the next one would be when N equals 2668, which is a frequency of 400.2 THz. We can plot all allowed frequencies, as we know 150 GHz will separate them. The plot will look like this. Here we have N equal to 2667, and the corresponding frequency of 400.05 THz. Here is 2668, 2669, and so on. These are the frequencies that are allowed to resonate in this laser cavity. So if you wanted your laser to have a frequency of 400.1 THz, you would first have to change the cavity length for this to be allowed, as it is not possible in this red laser's cavity. About 2600 frequencies in the visible spectrum would be able to resonate in this red laser's cavity. Now, there is slightly more to the story about these allowed frequency lines. We have assumed the mirrors are perfect, which is practically impossible. The imperfectness of the mirrors and other slight variations add a thickness to the frequency lines. The actual allowed frequencies in a laser cavity looks like this. Again, this is due to imperfections. The last piece of the puzzle is to mention the gain medium itself. Gain medium is just the material we are using for our laser. Different materials will have different energy levels, hence photons of different energy will be released during stimulated emission. For example, different materials will need to be used to create a blue laser than that of a red laser. Since the energy levels in a material are discrete, one would think that exactly one frequency would be emitted out of a laser, but only if this is also a frequency allowed in our laser cavity. We can superimpose these ideas on this graph. We assume here that indeed the stimulated emitted photon is a frequency that is allowed in the cavity. However, there is much more to the story. The frequencies being emitted out of the laser actually takes a shape like this. This was briefly mentioned at the beginning of this video when discussing line width. What is going on here are complicated events such as the Doppler effect, Stark effect, and other quantum mechanical behavior. The takeaway is that the gain medium does output a small range of frequencies, and has this gain curve. It is still extremely narrow, and said to be monochromatic. It's not, but it's close enough. To sum up, certain frequencies are allowed to exist in a laser cavity. There is some relaxation to these frequencies as the mirrors and such are not perfect. The laser gain medium emits photons in a certain frequency as well, but again there is some broadness to this as certain effects influence this. We can superimpose these two frequency plots and get the following. The frequencies under the gain curve that have enough intensity to overcome other cavity losses are the ones the laser emits. There are plenty of laser active medium these days. Any frequency you wish to lace is pretty much possible. Here is a picture of different laser material, and the frequency they output. Some are in the gas state, some solid, and it is even possible to use a liquid as a lacing material.
Medical fields determine the laser radiation energy utilized. And here you can see that low energy from 0.5 up to 3 milliwatt is sufficient for the intense therapy, relax therapy, and the middle energy laser radiation from 200 up to 2000 milliwatts is just for the physiotherapy, particularly endoscopy, and surgery and cosmetology. These medical procedures require the higher than middle energy laser radiation. At the next slide, you can see the different levels of laser radiation energy causing specific effects in tissues. These photothermal, photochemical, that effects of the laser radiation in tissue may be achieved. These effects determine the medical scopes for different laser implementation. Some examples of the medical laser applications are shown in this slide. Let's consider some examples of lasers applications. The argon laser, because the argon is the laser medium, has been successful in treating eye disease, which results from diabetes. The laser is able to stop the bleeding, which results and prevent blindness. This is illustrated at the diagram. The argon laser radiation of 0.1 joule energy is delivered in time of 1 millisecond over the area of 10 to the power minus 3 millimeter squared to repair small teeth in the retina by photocoagulation. It is referred as spot welding. One more example of the implementation of the argon laser. And there is the possibility of producing a spot of laser light small enough to carry out surgery on chromosome, destroying genes responsible for inherited abnormalities such as hemophilia and cystic fibrosis. These are some of the applications of the lasers for precise surgical operations. One more example, it is the carbon dioxide laser that is used for cutting surface skin and for delicate surgery on the brain and the fallopian tubes. The neodymium laser is used for internal removal of blockage And one more example of the implementation of the argon laser, it is drilling inside the ear. It can be used to remove a tumor or to free the movement of the small bones into the middle ear, as it is shown at this diagram. The present development work is concentrating on the possible use of lasers in treatment of cancers. One approach is to inject into tumor a chemical that is particularly sensitive to light, photoactive substance, which the laser would then react with, making the chemical toxic to tissue. This technique, called phototherapy, it is beginning to emerge from the development stage into hospital use. The diagram of these phototherapy stages is shown here. The lecture is on the quantum mechanics. Quantum mechanics is science dealing with the behavior of the matter and light on the atomic and subatomic scale. It attempts to describe and account for properties of molecules and atoms and their constituents: electrons, photons, neutrons, and other more esoteric particles such as quarks and gluons, as it was said. These properties include the interaction of the particles with one another and with electromagnetic radiation such as light, X radiation, gamma radiation. Quantum mechanics description of matter behavior on the atomic and subatomic scale was demonstrated by laser radiation mechanisms that we considered. The generation of X-rays is one more example of particles interactions result, explained by quantum mechanics. X-rays are used in some branches of medicine, so you should be familiar with the X-rays' nature in some detail. We start the third lecture point, the X-ray CT imaging. But before we will talk about just the medical imaging implementing the X radiation, let's consider what is the nature and how it is generated, X radiation. At this diagram, you can see the diagnostic X-ray tube block diagram. Diagnostic X-rays are produced by firing high-speed electrons at a metal target in an X-ray tube. The electrons are first emitted from a heated filament by a process called thermoionic emission. These electrons are then accelerated across the evacuated X-ray tube under the action of a large voltage across the tube. The filament forming the negative cathode and the target being the positive anode. On striking the target, the electrons lose most, about 99% of their energy, in low energy collisions with the target atoms, resulting in a substantial heating of the target. The rest, that is, of 1% of the electron energy, reappears as X radiation. It is the block diagram of X-rays tube and the stages of the generation of X radiation. Actually, it is the process of the transformation of the mechanical energy of moving electrons into energy in form of heat, 99%, and into the X radiation, electromagnetic energy. The X-rays emitted from the X-ray tube display a range of energies, enhance frequencies and wavelengths. The distribution of these energies is called the X-rays spectrum, which is usually presented as a function of photon energy, but can also be illustrated as a function of wavelengths. X-rays are originated through two different mechanisms, and each contributes its own special features to the final spectrum. The first mechanism of the generation of these, that is named as continuous X-radiation spectrum. The incident electrons pass close to the positive nuclei of the target atoms and decelerate, break. The incident electrons' kinetic energy is converted into photons of electromagnetic radiation known as breaking radiation. These photons have a continuous range of energies up to the maximum that equals to the energy of the incoming electrons, equals to product of the electron charge and voltage applied into the X-rays tube. It is continuous spectrum or breaking radiation. Superimposed on the continuous spectrum is a number of sharp intensity peaks, constituting a line spectrum. The lines occurs in groups. The shortest wavelengths, highest energy group being called the K lines, the next the L lines, and so on. These lines are a result of bombarding electrons penetrating deep into target atoms and ejecting orbital electrons from the innermost shells, the K or and L shells, near the nucleus. Electrons from outer orbits subsequently make transitions to fill the gaps in the inner shells, thereby emitting photons that energies are characteristic of the target atom. Transitions terminating in the K shell give rise to the K lines. Those terminating in the L shell produce the L lines, and so on. As long as the target has a high enough atomic number Z, the resulting photon energy will be in the X-ray range. The short wavelengths cut off an X-ray beam is determined by the tube voltage, and electrokinetic energy equals to the product of the charge of the electron and the voltage applied. Photon energy equals to the Planck constant times the line frequency. So consequently, when we take these two together, we obtain the short wavelength cut off of an X-ray beam. So we consider the generation of the X radiation, and now it is of importance to recognize the mechanisms of X-rays interaction with the matter, and these mechanisms are determined by the photons' energies. Let's start from the low energy photons, between 1 and 20 kilo-electron volts. Low energy photons simply bounce off an atom with no change in momentum. This is shown at the diagram. It is the simple scattering. The scattered and incident photons are coherent. This process is largely insignificant in radiography. Look at this slide where you can see X-ray photon that has an energy from 1 to 30 kilo-electron volts. It is energy equivalent to the K-shell binding energy of a matter atom. Then the photon will be totally absorbed and an electron ejected from the atom. The atom is ionized, and in this excited state, higher orbital electrons returns to the K-ground state with the emission of characteristic X-ray line. It is photoelectric effect. The absorption is important in soft tissue in the energy. Photoelectric effect. When energy of the photon rises and becomes between 30 kilo-electron volts and 20 mega-electron volts, about Compton scattering should be set, because at these energies Compton scattering is the dominant absorption mechanism. X-rays photon energy is much greater in this case than electron binding energy, and only part of the photon energy is given up during the interaction with an outer valence electron, which is effectively free. The photon continues in a different direction with diminished energy, and the recoil electron dissipates its energy through ionization. Compton scattering. One more photon is produced, but it is not coherent with the original X-radiation photon because it is of less energy. Scattering means the change of the direction of the propagation of the photon that is produced after interaction with the material, with the material's atoms. When the energy of the incoming is larger than 1.022 mega-electron volt, then the photon can interact with the nucleus of the atom, producing an electron-positron pair. Subsequently, the antiparticle annihilates with another electron to produce two 511 kilovolts photons. This is shown at the diagram of this slide. This effect dominates at high energies and is only important in tissue above 5 megaelectron volts energies. Pair production. This is the fourth mechanism of the interaction of the X radiation with the matter atoms. The list and the graphs illustrating the X radiation matter effects are shown at the next slides. The change of the X radiation intensity after the crossing layer of a matter is calculated by formula shown at this slide. So, be considered the details of the mechanisms of the interaction of the effect of X radiation in material, in matter. Now we can consider this process in terms of intensity of X radiation. What is the intensity? Let me remind you. It is just the energy carried by X radiation per unit time through the unit cross-section area of the material. For a non-divergent homogeneous beam of X radiation, the decrease in intensity of the beam in passing through a film of material is proportional to the thickness that is marked here by X and linear absorption coefficient of a material. It is marked here by letter mu. This is constant for a particular wavelength passing through a particular material. It is large if Z is high. It is usual practice to quote the half-value thickness rather than absorption coefficient of material. The half-value thickness is defined as the thickness of an absorbing material which reduces the intensity of X-ray beam to 1/2 of the incident intensity. The implementation of X-rays in diagnosis is based on the registration of X radiation intensity after radiation crosses the human body to obtain contrast images of internal structures. Photoelectric effect is the dominant mechanism giving the best contrast pictures. X-ray CT imaging, computer tomograph imaging. This is a technique for producing an image of a slice of the object, thin layer. At its simplest, it is a way of arranging to have one plane produce a clear image, regions above and below being blurred. Since X-rays can't be focused by lenses, this is arranged by moving the X-ray tube and the film cassette. The two are connected mechanically so that as they move, the image of the chosen plane stays in the same place on the film. As it is shown here, the image A stays as A prime. Objects not in this plane, such as B, are imaged in different positions as the unit moves from B prime to B2 primes. This is the idea, the principle of the X-ray imaging technique. And now, please, let's recognize principles of computed tomography. The task is to make an image of a section of a body from measurements made around the axis of the body. The plane is divided into small volume units called voxels. Intensity from a given voxel, called pixel, is reconstructed from the measurements made along a series of strips across the whole plane. The total intensity measured along the strip is simply allocated to each pixel in that row. The collection, reconstruction, and display of the scan data requires a powerful computer and sophisticated peripherals and software. The image reconstruction of each pixel intensity value is a result of about 1 million computation. The image is displayed on a TV screen to produce a picture of the slice scanned with variable contrast and brightness. It can be stored in the computer memory and used to construct a slice in a different plane in combination with all other pixel data. The X-ray source must highly collimated to produce the precise paths required. Typically, each strip of image is only a few millimeters wide. This means most of the radiation energy is wasted. The tube voltage and exposure are greater than for conventional radiology and radiography. Typical values are: the X-ray tube voltage is of 130 kilovolts and the tube current is of 300 milliamperes per second. Therefore, a great deal of heat has to be dissipated from the anode. Because of the tube movement during scanning, they tend to fail after a few months. In service and replacements are a large expense in the running of a computer tomography department. The video fragment will support this description, and you can take it.
A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
And finally, the summary of the lecture. This is quantum mechanics theory justifies laser radiation effects on substances and its correct use in medical practice. Quantum mechanics theory develops the scientific base for correct implementation of the X-radiation in medical practice. And we complete with the list of the information resources, including the video fragments that can support this lecture. We finish. Thank everybody for the attention.